In video 1 of section 4.4, we went over how to factor polynomials, where you first take out a common monomial, and then we went over sum of difference of cubes. Remember to look at things in this order that I listed here. Look for GCF first, and then if there is a GCF, take it out, and what's left over? Is it special factoring, like sum and difference of cubes, difference of squares, or a perfect square trinomial? If there is no special factoring, then count the terms. If it's 3 terms, it could be an easy trinomial, a hard trinomial, or a trinomial in the quadratic form. If there's 4 terms, you're going to want to factor by grouping. So let's try that now. In example 3, I notice there are a lot of z's, but I cannot take a GCF of a z out. But I do notice it's got 4 terms. So what you want to do is group up the first 2 terms together and the second 2 terms together. Now looking at the first grouping, you have a GCF now of z squared. So I'm going to take a z out, z squared out, and I'm left with z plus 5. In the next group, I'm going to look for a GCF, and I could take a 4 out, and a lot of times we'll take out this negative with it. That way we start, what's left over will be a positive z and a positive 5. Notice what's left over will be exactly the same as what I had left over from the first grouping. So together the z plus 5s will factor out and come together as z plus 5, and the other factor will be the little GCFs that I pulled out, z squared minus 4. And that's factored by grouping. After you've factored by grouping, I would just double check to make sure nothing can be factored again. Z plus 5 cannot, but z squared minus 4 is actually a difference of squares. So I'm going to carry down my z plus 5, and z squared minus 4 can be factored down to z plus 2, z minus 2, which cannot be factored again, so this will be my final answer. Next, factoring polynomials in quadratic form. If you look at example A, look for a GCF first, which we can't take any x's out, no numbers. It kind of looks like some perfect squares, maybe a difference of squares. Especially if you kind of want to ignore that this is an x to the 4th, and imagine it were 16x squared minus 81. Okay, even though it's a 4, it kind of looks like this. And this would be a difference of squares where we would have 4x minus 9 and 4x plus 9. But we didn't start out with x squared, where we have x times x will give us x squared. We started out with x to the 4th. So instead we'll have x squared times x squared, which will equal x to the 4th. Once I've factored once, check to see if I can factor again, and this first factor is another difference of squares, and that can be broken down to 2x minus 3, 2x plus 3. But remember, in the next factor, this is a plus, so that cannot be factored. There is no such thing as a sum of squares, only a difference, and this will be our final answer. Now let's try example 4b. I'm looking at this trinomial. I see a lot of p's going on. In fact, my GCF can be a 3p squared. What I would have left is p to the 6th plus 5p cubed plus a 6. I'm going to carry down my GCF and look at what's left, this trinomial, and decide if it can be factored again. It kind of looks like a trinomial. If I were to rewrite it like p squared plus 5p plus 6, I'm pretty comfortable factoring this. In fact, it would be p plus 3, p plus 2. 3 times 2 will multiply the 6, and that'll add to the 5. And p times p is p squared, but I need to get p to the 6th. So if I change this to p cubed times p cubed, p3 times p3 will be p to the 6th, which will work. So my factors here, factors of 6 will be 3 and 2, plus and plus. What 2 things in the front multiply to p to the 6th, and that'll be p cubed and p cubed. Looking at what's left, p cubed plus 2, p cubed plus 3, decide if it can be factored again, which neither one can, so I'm finished.